How do we prove this without using the Taylor series? So this was asked by someone in the comments, and gosh, this will be a long video. So first, let's let this part equal a constant z. So I'm going to write it like this with the I sitting over here. And we know that this z can be represented in polar form. So I'm just going to use alpha here because we already have a theta. But let's find what r and I alpha are. And we know that when we have this magnitude, we just square each of the terms and take the square root. And I'm just going to write this as to the power of a half. So now let's find alpha. So let's draw this in the Gantt diagram. So now we know that this is going to be alpha. And now let's squish it into this form. So you know that z is this. So now let's find the limit as this to the power of n as n approaches infinity. So what we're going to do is raise z to the power of n. So we apply this to the power of n. Let's use De Moivre's theorem. So De Moivre's theorem states that the magnitude gets raised to the power of n and the angle gets multiplied by n. So this gets raised to the power of n and this gets multiplied by n using De Moivre's theorem. So now to evaluate this limit, let's take the limit of this as n approaches infinity and the limit as this exponent as n approaches infinity separately and prove that that equals that. So let's split this into two. So I just squished the exponent here, but we can see as n approaches infinity, this will get bigger and bigger. That means that we're dividing by a bigger number, which means that the whole thing over here is going to go towards 0. So now we know here, we are left with. And this is just a really easy limit. So as n becomes bigger, n on 2 will also become bigger. So this is just equal to 1. Great. Now let's find the limit as n approaches infinity.